The normal tangential coordinate system is used when the path of the motion is given in the premise. Learn more about this coordinate system here in Dynamics of Rigid Bodies. When the path along which a particle travels is known, then it is often convenient to describe the motion using n and t coordinate axes, which act normal and tangent to the path respectively, and at the instant considered have their origin located at the particle. Since t and n are axes, let's identify the positive direction from the negative. Positive tangent follows the direction of motion, and the normal axis will always be positive towards the center of curvature. With the displacement s as a function of time, the particle's velocity has a direction always tangent to the path, and magnitude is determined by taking the derivative of the path, ds over dt, or simply notated as s dot. Velocity is a tangential component. Acceleration is the root of the squares of both the tangential and normal accelerations. Tangential acceleration is the derivative of velocity, as it depends on the magnitude. Also, it is computed from the formula AdS is equal to VdV, when the three variables are given. The normal acceleration is computed as the square of velocity over the radius of curvature. There are special cases of motion that can be depicted in most problems. The first case is when a particle moves in a straight path instead of a curve. The radius of curvature of a straight line is infinity. So if we solve for the normal acceleration, the square of velocity upon infinity is 0. We take the magnitude of acceleration from the formula, the root of the square of tangents and normals. It would be simplified as just the tangential component. The tangential component of acceleration can then be described as the representation of the change in the magnitude of velocity. The second special case is when a particle moves along a curve, but it moves in a constant speed, which would mean that the tangential acceleration is 0. Similarly, the magnitude of acceleration as the root of the square of the tangent and normal accelerations would show that it is purely the normal acceleration, which is the square of velocity over rho. Again, the normal acceleration always directs towards the center of curvature. Thus, it is sometimes called the centripetal acceleration. Summarizing the two types of acceleration, the tangential and normal, a sub t is the derivative of velocity, and also it is taken from the formula AdS is equal to VdV. In cases when the tangential acceleration is constant, integration can come up with the following motion equations. The normal acceleration, on the other hand, uses a single equation involving the square of velocity all over the radius of curvature. Furthermore, if rho is to be determined, it is equated as the root of the cube of 1 plus the square of velocity, and everything will be over the acceleration. Let's showcase the use of this coordinate system. First example has a boat traveling along a circular path of 50-meter radius at a velocity of 0.0325 times t squared, where t is in seconds. It is required to find the magnitude of acceleration at t equal to 10 seconds. The magnitude of acceleration is a, which is equal to the root of both the squares of the tangential and normal components. Given v as 0.0325 t squared, the tangential acceleration is its derivative, which turns out as 0.0325 times 2t. When t is 10 seconds, the tangential acceleration is 0.0325 times 2 times 10, which turns out as 0.65. The normal acceleration is the square of velocity over the radius of curvature, which can then be taken as the square of 0.0325 t squared over 50. And again, applying 10 for t, the normal acceleration is 0.21. Thus, the magnitude of acceleration is the root of the square of 0.65 plus the square of 0.21, which is equal to 0.68 meters per square second. The second example discusses a car traveling up a hill with a velocity of 0.2 s. S here is in meters, measured from point A. We are again to determine the magnitude of acceleration when s is 100 meters and ρ is 300 meters. With the general formula for acceleration as the root of the squares of a sub t and a sub n, we needed to look for both components. For the tangential component, check that velocity is in terms of s, and we are to look for acceleration. So we solve for the tangential acceleration with the formula AdS is equal to VdV. From this equation, we get a sub t as VdV all over ds, where v is given as 0.2 s. When s is 100 meters, we get the tangential acceleration as 4 meters per square second. The normal acceleration is the square of velocity, which is the equation 0.2 s all over ρ, which is 300. The normal acceleration is 1.33. Knowing these parameters, the magnitude of acceleration is the root of 4 squared and 1.33 squared to have 4.22 meters per square second. Another example has a crate sliding down the curve and we focus at x equal to 10 meters. The crate is sliding down at a velocity of 5 meters per second and its acceleration is 1.2 meters per square second. We are tasked to determine the direction of the crate's velocity and its magnitude of acceleration. Starting with the direction or angle of velocity, we take the slope, which is indeed dy all over dx, and this is the tangent of the angle theta. Theta is then the arctangent of the derivative of y, which is given as x squared over 24. It can be simplified as 2x over 24, where the 2's cancel out to have x over 12. Given in the problem is x as 10 meters. So theta is the inverse tangent of 10 twelfths and theta is 39.81 degrees. Next is to solve for the magnitude of acceleration, that is the root of a sub t squared and the square of a sub n. A sub t is already given as 1.2 meters per square second. A sub n is v squared all over ρ. Velocity is given as 5 meters per second, but we don't have ρ. Though we know the formula of ρ with one that involves the first and second derivatives of displacement y. With y as x squared over 24, we take its first derivative as 1/24 times the derivative of x squared. This can be simplified as 2x all over 24, which can then be further reduced as x 12th. The second derivative can be taken as the derivative of x all over 12, which is simply 1 all over 12. With the raw equation, we can plug the values of x 12th and 1 12th into it. With x known as 10 meters, we can finally solve for ρ as 2.03 meters. Knowing ρ, we can compute for the normal acceleration as the velocity of 5 squared all over ρ, which is 2.03, resulting to 12.33 meters per square second. The magnitude of acceleration is then computed as the root of 1.2 squared plus 12.33 squared, which is 12.39 meters per square second.